welcome everyone, people who are here online now and colleagues kind of watching this in the future. This is a GEReCo webinar. GEReCo being Geography Education Research Collective, our kind of small group of geography education researchers. And over the last few years, been really kind of honoured to be joined by so many brilliant people doing research that has been kind of really kind of interesting to geography teachers, and research that's kind of often like pushing some of these boundaries in kind of academic discipline and academic research related to things that are then being taught in schools. Today, Nick Leach is joining us. Nick's a postdoctoral researcher within the Predictability of Weather and Climate Research Group at the University of Oxford, amongst lots of other things, and explores the use of operational weather forecasting models within this field of extreme weather attribution, with a particular focus on heat events and storms. I encourage you to have a look at his PhD thesis on reliable attribution and projection of extreme heat events altered by human influence on the climate. And it's currently exploring various things that I'm sure we'll get into. And there's also a climate scientist at Climate X. And Nick, thanks so much for giving it your time and joining us in here. Over to you.
Thanks very much, Steve, for the introduction. Yeah, I'm not exactly sure how long this presentation is going to be. I'm sort of expecting it to be 15 to 20 minutes or so. And yeah, I've got to admit, it's a bit of a rehash of a talk I've previously given. So some of the stuff's a bit out of date, but hopefully the aim behind this talk will be to give a bit of an introduction to the kind of methodologies that underlie some of the kind of the newspaper headlines that you might see from time to time. But yeah, I'm basically gonna be kind of going off this theme of what's up with the weather and how do we try and understand how climate change is affecting not just kind of the climate in general, so like general weather if you average it over lots of days, but also like specific extreme weather events. So this is one of the slides that is going to look a bit out of date because the three events that I picked up at the time that I made these were the Pacific Northwest heatwave. So this happened back in June, at the back end of June 2021. It was a heatwave in kind of British Columbia, so the west coast, like northwest coast of the US or coast of Canada. Temperatures hit 49.6 Celsius in Canada, which kind of as a reference, it's not too far off the same kind of latitude that the UK is at. So you can tell that it was a pretty extraordinary event, and it was one that surprised, I think, many climate scientists kind of actively work in this area. I found it a particularly interesting event. I spent a lot of my PhD looking at it. And so, yeah, that's one example of an extreme weather event that at the time I made these slides was kind of particularly prescient. Another one was Hurricane Ida. So the remnants of Hurricane Ida had just caused severe floods in New York. And that was another thing that, I mean, nowadays, generally, whenever there is some sort of extreme weather event, you will tend to see it being linked in some way or another to climate change. And that was another one that at the time was discussed in the context of climate change. And the last event that I'd picked up on at the time were the Westphalia floods in Germany. So severe rainfall in both Germany and Belgium, leading to extreme flooding. And so because of the devastating consequences that extreme weather events can have and often do have, the question has been posed for quite some time now, so for several decades, of is climate change affecting the frequency or the intensity of an extreme weather event? And so just to start off with a summary of the state of kind of the broad state of climate science. So we're going to look at the kind of consensus picture of how we understand what climate change is doing to these kinds of extremes. So this is a really neat graphic from the Intergovernmental Panel on Climate Change, which, if you aren't familiar with them, every sort of 7 years or so, they provide an incredibly extensive review of kind of all sorts of basically the entire state of climate science, more or less. So it's the physical science of climate change. And so in their last cycle, which had kind of just been released back in 2021, this said that broadly speaking, so if you average over events all over the world in lots of different regions, then as we understand it, we kind of pretty confidently can say that heat waves are getting more frequent, they're becoming more intense, and the most intense heat waves are becoming kind of even more frequent than sort of just mildly severe heat waves. So, for example, something that most people would expect to see once in their lifetime, so a 1 in 50-year event. So you'd expect on average for most people to only experience that kind of event once. That's now expected to occur around every 10 years. And now if we move on to other sorts of extremes, so heat waves in general, this is kind of give it like glossing over a lot of the finer points, but heat waves we're pretty confident about in terms of the state of the science. And then as you get to kind of smaller scale events, so things like really small scale precipitation events, or things that are much more kind of, well, I don't want to say meteorologically complex, but thought of as being more complex, so things like hurricanes or tropical cyclones, in terms of how confident we are and what climate change is going to do to them, that goes down. So heat waves we're very confident, and then for things like precipitation, a little bit less confident, although still kind of relatively confident in the broad picture. So in the big sense, if you average over lots and lots of events, we would expect them on average to be getting more intense. And the other one on this slide is looking at droughts. So a particular way of defining a drought, so agricultural ecological droughts are also becoming on average more frequent. And this is, basically a very quick overview. And if you want kind of the full picture, you can look into the IPCC's 6th assessment report. These figures are in there. They provide really kind of good syntheses of the science, which are much more kind of easily accessible than the whole report, which is, I don't know, something like 2,000 pages long. It's a massive report. And so, what am I going to cover today? So I'm going to be going into some of the technical details of how kind of the basic picture of how scientists like myself carry out the analyses behind headlines that you've probably seen. So headlines like this one, which again, back in 2021 was pretty recent and most people would be thinking about it, but more recently, I'm trying to think of an event. It might have been something like, you probably saw it back in January, the LA wildfires. There were a lot of headlines that came out about how climate change was affecting those. And so I'm going to talk about actually what goes into those numbers that you see in the headlines. I'm going to split my talk into 3 parts. So the first bit is going to go over conventional attribution, which is like basically the kind of most mature way of coming up with these numbers that is behind most of what you will see in the papers and referred to. And then I'm going to talk about something called storyline attribution briefly, which is a slightly different way of kind of posing the question of how is climate change affecting a particular extreme weather event. And then finally, I can talk about the kind of the work we're doing here at Oxford. I'll probably go over that relatively briefly, and if people are interested, you can ask questions. But I think the first 2 are probably going to be the most interesting for this group. So conventional attribution. So this is the question that was probably, which often people tend to first think of. And this is the kind of first way that this question tended to be posed back in the kind of the late 90s. But it's actually an incredibly difficult question to answer, whether we like basically to say definitively that a particular weather event with all of the kind of complexities and non-linearities in the weather, to say that any given weather event is like caused by climate change is very difficult. Because basically what they're saying is this event impossible without climate change? And so for some things, that might be more true. So at some point, there will be some events like storm surges, where just because of sea level rise having risen to a certain point, I mean, hopefully, to be fair, we don't get to that point. But if global warming increases to a more and more into the future, then sea level rise will basically push some storm surge events beyond where anything that we could have even got like possibly achieved in the recent kind of historic past. And so then we probably could say reasonably that it was caused by climate change. But there are an extremely limited number of cases like events where this might be the case. And so for the vast majority of extremes, most climate scientists would agree that they're not directly caused by climate change. And so instead, we tend to ask how climate change is impacting these events by making them more extreme or less extreme for some cases. So for things like cold snaps, it's generally understood that they're actually becoming less intense. Or the other way you can ask this question is climate change making them more or less frequent? So are we getting more heat waves than we were before? And I'll cover in sort of fairly broad sense how we try to answer these questions. So the title of the slide, is there is no planet B. And what do I exactly do I mean by that? So in climate science, we can't perform kind of an experiment in the real world to work out what would the climate look like in 2025 without human influence, because of course the climate that we have in 2025 has got human influence kind of baked into it. And there is no spare Earth where we could perform this kind of experiment. And so to determine what a climate without human kind of influence on it, so without man-made greenhouse gas and aerosol emissions, to find out what that would look like, we tend to turn to climate models. So these are like incredible feats of engineering. And I think either last year or the year before, the two people who were instrumental in the early work of climate models won the Nobel Prize. And so basically we take all the information, all the physics that we understand about the atmosphere, the oceans, and other parts of the Earth system. So you'd have things like ice sheets in there, things about the land surface, the biosphere, take everything that we know and basically try and create a model of that within a computer, and then use that to simulate as accurately as we can. And that's a big kind of caveat, the Earth's climate within a computer. And then you can perform experiments because you've got a model of the Earth's climate where you can say, well, actually, what happens if I remove all of the human influence on this climate? And so these are some of the equations that would go into a model like that. So these are the Navier-Stokes equations that describe how fluids move, and both the atmosphere and oceans are fluids. And so these are kind of some of the fundamental equations behind that. And this is a schematic of what a climate model kind of looks like. So to reduce the complexity of the Earth system so that computers can actually solve equations like these ones, we tend to divide the Earth up into lots of little boxes and then solve the equations in each of these boxes, which can kind of talk to each other and then transfer, like basically evolve the state of the climate forward, moving things like temperature around and like air parcels and understanding how kind of the pressure changes in the atmosphere and that kind of thing. And so, yeah, climate models are fantastic and are like an incredible kind of feat of climate science, but they're certainly not perfect. And that's something that motivates some of the later parts of this talk. And so let's go on to the steps that scientists take to kind of produce those numbers that you'll see in the headlines and in the reports. So let's take an event. So this is an event that I looked at relatively early on in my PhD. It was the summer of 2018. It was a very hot summer at the time. I think 2019 may actually have ended up being hotter, so it wasn't particularly extraordinarily hot for that long. But so you take your event that you're interested in, and then what you do is you run a large ensemble. So basically run one of these climate models that I've just described lots and lots of times. So to produce a really large kind of sample of what the weather might look like. So what we run the model in both this kind of setup where you have all the human influence on the climate. So all of the kind of human greenhouse gas emissions, you add those into the model and the effects that those have on the radiative balance in the atmosphere and things like that. And then you run a second version of the model where you've removed those. And so you run both of those kind of setups of the model lots and lots of times. And then that builds up basically a picture of what all the different states that the weather could take within those two different kind of climate states. And so that's what this figure tries to show out. So on the right, you've got lots of different basically summers. I think this is probably summer average temperature, but lots of different effectively summer climates within the real world, and then you've got lots of different summer climates within a world where you've taken out human influence. And so what we can then do is we can define our event in some way. And so this, I think, is taking instead, like, as it is, you could do this at every point on that map, but typically you will see that the event, like, you have to define your event in some way. And so for the purposes of this talk, I've taken, I think, the average summer temperatures over the UK. And so then you can collapse those maps down into single points. So one for each of the, like, the samples that you have from your climate model simulation. So you run them a lot of time. So you've got lots and lots of years of data. You then create the, like, basically the statistic for each of the years and produce these distributions. And so then you can do some analysis, which I'm going to talk about next. So in this plot, you've got two distributions, which are basically all of the different summers that you've simulated in both your real world version of your climate model and your no human influence version of your climate model. And yeah, the red one's the real world, the blue one's the world without human influence. And then on the y-axis, you've got the frequency with which particular temperatures occur. And so what you do next, or well, what is often done next, is I can add on a line that shows where the kind of the event that you're actually interested in was. So this was the temperature that we saw, I think, in 2018. So actually not huge, like not hugely extreme, but yeah, this is the observed temperature. So that's the black line. And so what we can now do is we can work out, based on that real world histogram, we can work out what the probability of our extreme, like, of seeing that event is. So just look at the, I mean, probability is basically area under a normalized histogram. So if you add up the total area on the histogram and then add up the area just to the right of that black line and then divide the area to the right of the black line by the total area, you get the probability of observing an event at least as hot as the one that you're interested in. So you can do that for the real world to get one probability, and you can do that for the one without human influence on the climate. And so in this case, that's smaller. And usually then the way that we express kind of human influence on the climate is to divide these two probabilities. So you've got your probability of observing the event in a world, in the real world, and the probability of observing the event in the world without human influence. And if you divide those, that gives you a ratio which represents how much more likely is it to see an event at least as hot as the one that has been experienced, so that black line, in a world with climate change compared to a one without climate change. And so this number, which is the ratio of those two probabilities, is the one that you will almost always see reported in the media, where when headlines are talking about likelihoods rather than sort of severities. So an alternative framing would be to say, well, if I look at kind of how much, like on average, how much hotter is my red histogram compared to my blue histogram, then you could produce a kind of a temperature that tells you on average how much hotter are these kind of summers becoming. And so that would be the way of framing it around severity rather than changes in likelihood. But most often you will see the change in likelihood. And so I can also, I think, if this is going to work, which I'm not sure it is, use this to kind of illustrate a point, which is that generally the more extreme your event becomes, the higher this ratio gets. And because at some point you will get to a point, if there is clear differences between the histograms, you will often get to a point where you basically don't have any events left in your no human influence one. And so this is basically saying that it's kind of, it does matter where your event itself lies. And so, but another thing to point out is that generally, if you kind of calculate some kind of how certain or uncertain you are about that ratio of the two probabilities, the more extreme the event, the bigger the uncertainties are, just because you're taking into account so much less data in effect. And so, right. This was basically a kind of simple introduction to how we come up with the numbers that you might see in the headlines. These often come from a group called the World Weather Attribution group, which in the wake of extreme weather events often does very rapid attribution analyses. It's kind of a consortium of scientists from around the world who, after a particularly noteworthy extreme weather event happens, they will kind of get together and collaborate to perform basically a more detailed version of this analysis, all working together, and do that as quickly as they possibly can, so that they can provide these numbers while the event is still kind of relevant. Because previously it tended to be done through peer review, which then meant that you had numbers for events that happened 1 or 2 years ago, and then basically no one's interested by that point, or often people are not interested by that point. And so there are a few details that I've skipped over though. So I talked a bit about defining the event. I said the numbers that you get are often quite dependent on how you define your event. So broadly speaking, if you define your event, so that I defined it by taking kind of summer average temperatures over the UK. If you have a long and very hot heat wave over a large region, it's a real question to say, well, how am I going to define that? Do I take the hottest temperature? Do I take the average temperature? What kind of spatial extent do I use? Should I look at each kind of little grid box in my map, or should I average over a larger rectangle? Because those choices can have big implications for the numbers that you get out at the end. And another important thing that is often done during these analyses is to make sure that any model that you use is consistent with observations. So this usually involves checking that model trends in temperatures, so how temperatures are changing over time, over a historical period where we've got observations, checking that those trends are similar to the observed ones. And then finally, there are lots of different climate models that have been built by different groups around the world, and often during these analyses, people use kind of many of them, so that to kind of guard against any one model being incorrect, you use basically more than one model to kind of have more robustness in your result. And the problems. So it takes a lot of computing power to run these climate models, the number of times that you need to kind of understand the extreme tail, which is what we're interested in here. And so often they have, they're kind of limited in their resolution, and therefore have kind of limits on the physical process that they can explicitly simulate. So kind of this creates a real problem for extreme weather events, because by their nature, extreme events are kind of exceptional and often involve lots of different processes coming together kind of optimally in just the right way to produce this really extreme event. So this means that even if a climate model is able to model the kind of average climate of the Earth, which is what they're originally designed for, really well, they might not be able to simulate a particularly important process for an extreme weather event that you're interested in. And I think this was broadly speaking the case for the Pacific Northwest heat wave, where it basically so hot and caused by some very specific physical process that hadn't really been seen in the observations before, that climate models don't really do very well. That means that using climate models to try and understand what climate change is doing to an extreme weather event that they can't really simulate, it poses a real problem. And the second question is, are we actually kind of attributing a specific extreme weather event? Because these distributions are made up of, I've kind of defensively taken the summer average temperature of the UK. That's a perfectly good way of defining an event, but naturally there are lots of different kind of meteorological setups within these distributions. And so some of these events that I have kind of included in the analysis might not actually be particularly relevant for the summer so in this case, for the summer of 2018, which might have had a very particular kind of meteorological setup. And so this then brings me on to storyline attribution, which was posed as a kind of an alternative framing to this kind of what this first half, the first half I've taught, is generally called the risk-based approach, where you compare these distributions. In the second one, you actually say, well, actually, I care more about the kind of synoptic, so the weather patterns that happen during my extreme. And so you ask the question of, rather than saying how much more likely is an extreme event of a particular kind, you say, well, if the exact same kind of weather patterns occurred in a different climate, so in a pre-industrial climate, how would that change the event? How would it change the severity of the event? And so this is how, if you might have seen, this is they're a bit more recent than the World Weather Attribution Project, and don't tend to get quite so much like media attention, but they are a group that are doing similarly rapid attribution studies in kind of in the wake of extreme weather events. And so they use this approach. They use one approach called analogs, which is basically where you take as much historical weather data as you can, and you look for weather patterns that look similar to the event you're interested in. You then kind of divide up your historical weather into two periods, so a like more distant past and a recent past, and compare how those, like what those analogs look like in each, and are there differences between the two time periods, and then say, well, if there's changes between the two, we can say that basically there's potentially climate change influence on those analogs. Another way is to use climate models and to kind of nudge them so that their weather patterns look similar to the ones that you're interested in during the extreme weather event. And then basically do a similar analysis where you then remove human influence, nudge the models again, and work out how the weather changes. But again, storyline attribution has challenges. So you've got the issue of model errors. Like if you're using a climate model, a nudge climate model, you've still got the problem of, can it actually do the processes that I'm interested in? And if you're using historical weather data, it's dependent on kind of the quality of your analog. So the weather patterns you picked out that look similar to the one that you're interested in, sometimes the one that you're interested in is so rare that you actually don't really have any analogs in kind of the recent past. And the last point is that this doesn't really answer your questions of risk. It doesn't say how is the probability changing. It just says how is the severity changing, unlike the risk-based framing, which does. And I think, yeah, so it only answers like, well, if the same event were to happen in a different climate, for a case of a heat wave, it would be, is it hotter or colder? And for rainfall, it might be, is it wetter or drier? Not, is it more or less likely to happen? And I think I'm going to actually stop there, and I can answer questions about what we're actually doing at Oxford, if there's interest. But I think in the interest of time, I'm going to stop there.
Awesome. Thanks so much, Nick. Let me give you a virtual and a real round of applause. Gosh, that's fascinating, and like a real kind of whistle stop. I'm sure it's generated, I've got about a million different questions, but it's kind of drawing in as well, and it definitely would be interesting to hear some of that stuff that's kind of going on at Oxford there. And David Mitchell in the chat has asked, do the models fail to account for very distinctive local characteristics? David, I don't know if there's anything else you want to Sarah, pose that question.
Not really, just thank you very much, Nick. That was really interesting. And yeah, I was just thinking, like the Northwest Pacific heatwave, is that part of the problem, that there's something going on that, the exact, shape of the mountains and in that part of the world that the models fail to pick up on, that can sort of tilt the events in an extreme way?
Yeah, it's exactly that kind of thing. And so generally these attribution analyses are done on events that are kind of the scale that in theory a climate model kind of could capture. I mean, in the case of the Pacific Northwest, the reason why I think there was a particular challenge was because, getting into a bit of the meteorology. So just before the peak of the heat wave, there was an atmospheric river that injected a lot of moisture high up into the very warm kind of moist air high up into the atmosphere, which basically primed it such that when you had this, this is kind of where we got heat dome from, but like high pressure system, it meant that the air was already incredibly warm and moist from the injection from the atmospheric river. And normally when that happens, you get it rains out. You might get like a flood extreme, and actually that happened later on in the year where similar kind of atmospheric river, but it didn't have the high pressure system, and so it did just rain out and created this basically flood conditions. But at the time, you got this coincident atmospheric river and high pressure system, which then meant that the warm air didn't rain out, but just descended and got even warmer. And that atmospheric river process is not generally well simulated by climate models, and it's that kind of slightly more complicated kind of dynamical processes that climate models often struggle a bit more with. But that's quite a large scale process that they struggle with, but they would struggle even more with things like attribution of severe convective storms is generally not done because climate models just don't have the resolution to simulate severe convective storms. So things like tornadoes, they don't simulate them at all. So there's kind of, you can use proxies, so you can use things like larger scale indicators of, oh, this is the kind of weather that might produce tornadoes, and you can try and do some analysis on that, but you can't kind of attribute they don't simulate tornadoes, so you can't really attribute changes in frequency of tornadoes themselves.
Can I ask, is that about the size of the squares that are used or the cubes that are used to? So what size are those cubes? Has that size changed? And
yeah, so it has changed over time. So in general, the kinds of models that are typically used for these analyses have grid boxes of order about 100 kilometers. So big, like they're pretty large. I mean, it's got better over time. So would have used to be that somewhere that, like, I don't know, back in, so one of the original studies that was done here at Oxford looked at kind of a pretty state-of-the-art model at the time, back in 2004, and I think it was about, the UK would have been about 4 of those boxes. So yeah, you're basically looking at four boxes of data, and so now they're about 100 kilometers, and so our work at Oxford has been about how can we actually use weather forecasts to do the same thing, because typically weather forecasts are run at a much higher resolution. So the model that I work with a lot is actually, those boxes are 9 kilometers. And so once you get down to those scales, you start to resolve a lot more of the processes that are important for these kind of extremes, and which is one of the kind of motivating factors for using weather forecasts rather than climate models, because they're more designed to simulate the extreme weather.
And it's just a computing power issue that means you can't use them? Yeah,
largely. So because climate models tend to be run for kind of, again, order hundreds to thousands of years, it's incredibly expensive to run them at because the cost of running a simulation doesn't go up with like the square as you might as well. Intuitively, you might have to go out with the square of the resolution because you've got 2 spatial dimensions, but actually because of the way that the numerics works, it goes up with the cube. So if you go from 100 kilometers to 10 kilometers, your model 1,000 times more. You've got this real trade-off, particularly when it comes to extreme weather, of you need a lot of data to sample the extremes. Otherwise, you've got no statistical robustness, but you also need the resolution to actually simulate the extremes well. So there's a massive trade-off.
When you say the cost of them, is there kind of a figure to how much it costs to run one of these?
I'm trying to think of whether I can express that I vaguely know off the top of my head how much it costs. So just the energy costs for the simulations during my PhD. So just the energy costs, not the costs of actually developing the model or like management of the computers or anything like that, were probably of the order kind of £10,000, and there's not a lot of, I mean, it doesn't sound like too much, but like it does. So
yeah, well, and so the time as well, there's those kind of like costs, but the time costs in terms of like the speed, that I imagine that's changed hugely over that time period. You're talking about stuff from like 20 years ago, that the kind of like nature of that computing power means that not only the complexity kind of increases, but the time decreases. Like, how long do these things take to run, and how's that kind of changed?
So to do kind of very long running climate model simulations, I mean, it depends on how big your supercomputer is, but probably of order like months to run the kind of simulations that they do. And I'm trying to think of, probably of order month just for the relatively coarse resolution runs. I mean, there have been calls from some people, like more people, some people at Oxford to basically put that more money. This is it. Like, climate change is a serious enough problem that we should put enough money in to be able to run high resolution models kind of, I mean, yeah, the idea is a climate change, like a CERN for climate change, where you basically, because in the grand scheme of like kind of research budgets, it's not actually that much. It's a lot that it would take to run kind of a very high resolution climate model, but it's compared to some, like, I don't know, research that goes into defense spending, and
Sure.
it's not a lot.
Yeah. No, that's fascinating. Sorry, I'm conscious that I've got so many other questions, but others, please do feel to free to kind of like use the chat or to turn the camera on and kind of come on. But David, just saying, if an event's 20 times more likely in current climate than pre-industrial, why not say yes, it's caused by human climate change? Because you have 95% certainty it would not have happened without human climate change.
Yeah, I mean, I think this gets into like how you're framing the question, but I think the difficulty that, well, I'd have with that is that even if it's 20 times more likely, it could still happen. And so you can get into, I mean, there's a whole kind of branch of like maths in causality theory and like called causality theory. You can get into kind of is like necessary versus sufficient causation, which some papers have been written about in the context of attribution. But I think as far as like most kind of climate science would see is if there is a chance that you could have had this event without human influence, then you can't say that it was caused by human influence because it was possible without it, if that makes sense.
Yeah, I hear what you're saying there. I'm not a proper scientist, if you like, but I mean, science operates on probability, right? So you're never 100% certain of anything. It just hasn't yet been disproved. So I hear what you're saying, that there's a chance this could have happened in a non-human world, but once you get to those levels of it's so much more likely to happen. It would simplify things a lot in terms of communication in the media, that when the question's asked, is this because of or caused by climate change, it was saying yes, it is, with the behind that the caveat being we're 95% certain. It would be a good sort of communications strategy, if you like, because it's sometimes when you see things on the news and you're thinking, well, of course this is so much more likely, of course it's connected to climate change. Just the simplicity of being able to say it's caused by human climate change might be helpful.
Yeah, I think if you're thinking about kind of confidence in, like, with the 95% certainty being a quite like standard scientific like benchmark, is that kind of the angle that you're coming from?
Yeah, like, I mean, there's levels of significance, aren't there? 99%, 95, but it sows, I think, the doubt when we hear, understandably, no, we cannot be absolutely sure that this was caused by climate change. It makes the message, I think, that can be picked up is, oh, the scientists aren't sure that there is climate change. Some people might interpret it in that way. So I just think it muddies the waters around the understand the confidence of the impact of climate change on events.
Yeah, I can definitely like sympathize with that. I think that the challenge is that the kind of where the uncertainty will be on that figure. So the headline might be 20 times, but the kind of confidence interval, or like where the uncertainty is on that number itself. So it's like, even though the central number might be 20 times, but it's probably somewhere between, I don't know, it might be between like 5 times and 100 times. And so that's where it gets a bit kind of, that's where the uncertainty actually is, rather than that being the kind of probability itself. So your 95% confidence, it's between 5 times and 100 times, rather than it being like a 95% confidence that it is climate. Yeah, if you see what I mean.
Yeah. Yes. Yeah, thank you.
It's good. And I think, yeah. Oh, you guys see.
No, go on. What were you going to say?
I was going to say, and I think in the kind of in the context of kind of the uncertainties that do exist, that we're very much more difficult to quantify. So things about these, like how well models represent some processes, they're not accounted for really in the kind of like in the uncertainties that most attribution studies will get into. So I think there's always a bit more kind of hesitation when you haven't sort of quantified all of the different sources of uncertainty, and there are particularly big ones around kind of model error, basically, because we know the models aren't perfect, but it's very difficult to say how much that adds to how certain we are, if that makes sense.
Is there in that kind of uncertainty, in that kind of model error, is there a kind of a general kind of direction of the error? Like, does it generally kind of like over or underestimate these things, or is kind of like just more kind of like complexity and that?
I'd say it's often kind of tricky to say. So one way in which often the models are kind of errors arise is in they underestimate the strength of so like links in the atmosphere. So there are processes that basically mean that if you get a certain, like, I don't know, if the ocean is in a certain state in the equatorial Pacific, so in the tropics, you get the, I don't know, particularly warm sea surface temperatures somewhere for some reason, then that has strong links to the weather somewhere, like basically somewhere else on the planet. It might be Europe. And so models often underestimate the strength of these kind of what are natural kind of connections between different parts of the Earth. And so that might be, if your model gets that wrong and you have an event that is an important process for, then you might end up saying, well, humans have kind of had more of an effect on this event than they might otherwise have done, because you don't have the kind of like the natural variability in there. So probably because of the way that those tend to work, you would on average end up saying that these, like, we might be overestimating, but that's a kind of I certainly wouldn't say that's always the case. And there are some there are other ways that I think generally the climate models that people use often underestimate things. So there have been some recent studies using very high resolution models, looking at kind of very short, very intense rainfall extremes, so sub-daily rainfall extremes, which climate models don't really simulate very well at all. And so some studies have suggested that these are actually getting far more severe, far more kind of quickly due to climate change than climate models would suggest, because they don't simulate the kind of those processes that are changing as a result of climate change. So in that case, we'll be underestimating.
Yeah, fascinating. I don't know if you can see David's question.
How much better can that? Yeah, so I think I'll repeat the question in case people aren't looking at the chat, but it was how much better can the models get and how quickly? So is things like AI helping? I think AI is a really interesting question. There's been a ton of work, particularly for someone who's kind of like myself, at the interface of climate and weather, where like AI has had a massive impact on like weather research that goes on over the last few years, because I think it's developed way quicker than I think people were expecting. We're now at the point where, broadly speaking, AI-based weather forecasts are outperforming physical models. So the weather center whose model I use, the European Centre for Medium Range Weather Forecasting, recently operationalized an AI weather model, because they are genuinely very good. I think it's a fact that I feel like a lot of meteorologists are a bit like annoyed about, because I don't know, you spent so long building up these like very, very complicated and incredibly good physical models, and then it takes 5 years to build a data-driven model that's kind of outcompeting almost. Though I would say that I certainly don't think they're going to replace them, because there are things that AI models don't do very well that physical models do, and they also, broadly speaking, AI weather forecast models depend on simulations from the physical ones to train them and to initialize them. So yeah, it's not the end of physics-based modeling at the moment, but that's weather forecasting. And so the climate is a very different question. So it's not asking to kind of, rather than for weather forecast, the AI question would kind of be look at a load of historical weather data and learn how it changes kind of from time to time. Whereas climate change is asking, well, like how is the climate going to respond to, like, based on the laws of physics, to a very small change, like broadly speaking, what is actually a very small change in the weather, like kind of in the weather itself. Because I mean, yeah, as you like, climate change in terms of global scales is around 1.3, 1.4 degrees. Temperature variability at a local scale is way bigger than that. And so you're now asking a data-driven model to try and detect that small change and understand what it's going to do. And so it's a very active field of research, is trying to develop a similar climate model based on AI. And I think, I mean, Google are one of the people that have worked on that a lot. And I think they found that you can get an AI model to kind of emulate a physical model pretty well. By doing some clever things about kind of doing some sort of hybrid of the two. So you have some elements of a physical model, and then you use AI to simulate some other elements, which are really expensive. And so you can make a much cheaper model that still kind of has some of the advantages of both. I think we'll see a lot. Like, I expect to see quite a lot of development, and I think it will certainly improve the efficiency of these models. So we might get higher resolutions quicker, because, like I was saying, like, if you have expensive things in your model that AI does well, you can replace those, but keep some of the more important physical processes, and then you can basically run your model at higher resolution or for longer, whatever. But I think one place, again, where AI will struggle is with kind of these really high resolution simulations. We actually don't have very much data. Like, we don't have observations at the scale of, like, what basically at the scale you need to get to start resolving some of the, like, important processes around rainfall. So convection, you need about 4 kilometers, and we just don't have, really, there aren't observations that cover the planet at that resolution for very long. And so you're kind of almost ending up back reliant on running a physical model to then train an AI model, which would be like, it's a thing that people are going to be doing, I would expect, for sure. And it might mean that we can, like, basically run these much longer simulations by training an AI model on some high resolution physical model, and then run it loads and loads more times because it's much cheaper to run. But I don't know, it will be interesting to see how it develops over the next few years, because it has kind of, yeah, it's fundamentally changed kind of the field of weather forecasting, and we might see a similar thing for climate, but it is a very different question. But it's a great question.
Thank you.
I've got this is such a silly basic question, but you're talking like in these like really binary terms about the different models, kind of weather models, climate models. Does it always kind of stay like that in this kind of like really binary sense? Do you get kind of models that kind of like do a bit of both, or kind of like some grayness between them?
There absolutely is. Like, kind of, there is really no difference between them, to be honest, in terms of like the equations they're solving, like how they're implemented, the kind of techniques used. There is really no difference, but I distinguish between them because practically weather forecast models are implemented to be able to simulate the weather as well as they possibly can, and they're validated extremely well, because the reason why weather forecast models are funded so much is because it's so important for so many aspects of society. Yeah. Have been basically verified and validated over the past however many decades to be as good at simulating the weather as we can possibly get. Whereas climate models have generally been a more academic kind of need to try and understand the climate, rather than to try necessarily. I mean, obviously we check to make sure they simulate the weather well enough, but it's harder to, especially because weather forecasts trying to predict the actual weather. So we have observations, whereas climate models are just trying to simulate something that looks as close as to the actual weather as possible rather than the actual weather itself. But yeah, there absolutely is a spectrum. So like typically as you go from, so the forecasts I work with are around like up to 2 weeks at that resolution. And then when you go beyond that, you get into, so they're called medium range, and then you get to sub-seasonal, which is sort of between 2 weeks and a month. And typically the resolution, you run models at that range, a little bit lower resolution because you don't get so many of the benefits. There's not much point. And then you get to seasonal, which is kind of up to like 3 to 6 months. And again, generally the resolution drops. So a seasonal forecast, like the state-of-the-art seasonal forecast might be around sort of 40 kilometers compared to the 10, but still better than the model. And then when you go beyond that, you generally end up kind of back more towards climate model resolution, because again, kind of the dry, like the things that you're trying to predict depend much strongly on the really good, like, because they're not like, we're not going to predict a really extreme heat wave to the day 6 months out. It's just not possible. We're looking at kind of much larger scale signals of that, like, oh, maybe it's going to, like, maybe this summer is going to be warmer than normal, which is information, but we can't, like, you can't predict the weather actually really 2 or 3 weeks.
Amazing. Can I just ask one last kind of question? And yeah, sorry for like probably dominating touch this. It's like Emma said in the chat, it's been like really super interesting. But the thing I was thinking about as you were talking earlier, and you used the number of kind of news stories, and it's really interesting, this kind of like notion of stuff being kind of dated or not dated, and then things from kind of 2021, which in some ways feels like kind of yesterday, is then kind of seen as being slightly dated. But so I was kind of thinking partly about that kind of datedness question, but also just your insights into these news stories in general. So you had some pictures of these kind of news articles. I'm thinking particularly of teachers using these news articles in the classroom. What would you kind of say to them? What would your advice be to these teachers? Are there things that they should be kind of looking out for with these kinds of stories? Are there things that actually you would say, look, you need to be questioning this with your students, stuff that these stories are like reporting really well, or things that you always get frustrated with, knowing more of the research? And yeah, what's your advice to kind of teachers using these news articles in their classrooms?
I think it's a tricky one, because like on the one hand I got into climate science because I thought it was like important problem, not just because it's interesting. It's like incredibly important problem that we all will face. I mean, probably less so in the UK than in some other parts of the world, but it will be catastrophic for people in some parts of the world for sure. But then on the other hand, is kind of the science is certainly not yet like settled, and especially in the terms of in the context of extreme weather. Like, we know that the models have deficiencies, and like, although like you can produce numbers like the ones that you'll see in the headline, but I do struggle, because typically the numbers that will make the most headlines will often be the largest, but not necessarily the most kind of robust or like scientifically accurate, just because of how the media operates. And I like attribution scientists do generally try and do a good job of communicating that. But as someone who has done media interviews, you don't pick what gets put in the headline. You can kind of caveat your results to death and say, well, we know that there are like lots of uncertainties. We know that we don't fully understand the system as well as we should. So there is uncertainty around these numbers. Sure, we know that climate change is having an influence, and that's kind of broadly speaking true for, like, I mean, there was an interesting paper back in 2015 that suggested that actually, instead of the null hypothesis being that climate change hasn't had an influence and you have to prove that it has, it should actually be, well, obviously we've changed the climate. It's every weather event has got some sort of climate change in. Right. It should actually be the other way around. But anyway, but I think I would kind of, they are like, it is important for people to know, but I think it is also important to kind of understand the context behind it, and that there is still plenty of science that needs to be done in order for us to make good decisions around kind of things like adaptation. Like, what adaptation did we, like, these numbers do actually do matter. They get raised in kind of political sphere in the context of adaptation. And so if you kind of overblow the impact of climate event, you might end up spending money in in ways that aren't effective, because actually the impact isn't so big, but for some other sort of extreme weather that we are less certain about, and so you don't get the headlines about, it actually does matter more. And so I think I have a kind of important, and I do think it is important, obviously important for people to be very aware of the impact of climate change on extreme weather. That's why I study it. But I think it would also kind of caution against people to be like, kind of, I don't know, dig into it, like read the reports in more detail, read things like the IPCC's report, which are usually pretty good at saying what we have high confidence in and what we don't. But yeah.
Awesome, thanks so much. I mean, I'm going to email you, because I think there'd be a great teaching geography or geography article to kind of get into some of these more to really help, because obviously it's such a fast moving field, and it, like you say, is kind of so important, so consequential, but also so complex, and he's done a brilliant job of kind of getting us into some of that. So thank you again very much for your time and for all of that, and I look forward to taking these conversations forward hopefully as well.
Cool, thanks very much for having me, Stephen.
Enjoy the rest of your evening. Thanks everyone. Bye.